So far, we've talked about 4 different indeterminate forms, and I have them up here on the screen right now. So we've got our 0 over 0. So when we're taking a limit, if we end up with something 0 over 0 or infinity over infinity out of a quotient, a limit of a quotient, those are indeterminate. And we've also talked about a difference. Infinity minus infinity is also indeterminate, and 0 times infinity is also indeterminate. So remembering that these indeterminate forms, I always try to think of these are where within the limit, the result of the limit is a power struggle. So the result of the limit is a bit of a power struggle. Like we're not sure who's going to be the winner. So the result of the limit is a power struggle. In a quotient, we're not sure if the numerator or the denominator is going to win. Struggle. Let me finish writing this out. So we're not sure if the numerator or the denominator is going to win. In a difference, we're not sure if the first function or the second function is going to win, or if it's going to be some kind of a balance. And so what we have is this rule called L'Hopital's rule, which we've been exploring in this section, that allows us to use the derivatives, the rates of change of the derivatives, to take the limits. And when we have one of these other two forms, infinity minus infinity or 0 times infinity, we do a little manipulation so that we can get it into the quotient form where we can apply L'Hopital's rule. So I'm going to highlight the two forms here that we can apply L'Hopital's rule in these forms. So now what we're going to do is take a look at 3 more indeterminate forms. So let's go ahead and get these up on the screen. So the 3 forms now that we're going to look at are in the forms of power. So when we're taking a limit of a function raised to a function, f of x to the g of x, as we approach a, and a can be infinite or one-sided if needed. And if we end up with something that looks like 0 to the 0, infinity to the 0, or 1 to the infinity, all of these are indeterminate forms. But none of them are in the quotient form. So remember, we can apply L'Hopital's rule if we have the quotient form, 0 over 0 or infinity over infinity. So what we need to do if we come across one of these power forms is we're going to have to do a little bit of manipulation. We're going to have to use a little bit of algebra technique, and we're going to have to get these power forms into a quotient form that we can apply L'Hopital's rule to. So that's what we're going to spend some time on some examples going through, and I'll walk through some steps for that. But just as a quick reminder, these are, once again, power struggles, because normally if you have 0, just a quick side note here, normally if you have 0 raised to a number, that's going to be 0. But as soon as and if you have a number, let's just explore that first one, raised to the 0, that normally generates a 1 for us. But when you have 0 to the 0, that becomes a power struggle, becomes a question mark. We don't know. That's an indeterminate form. So again, just kind of remembering that these indeterminate forms are the forms that are a power struggle, where we just don't have an immediate result. We have to do a little bit more work. So when we see these indeterminate forms, it should just mean, oh, I don't know, it's not obvious on this one. I'm going to have to do a little work, little manipulation, possibly apply L'Hopital's rule, and get myself to an answer for the limit. So let's just go ahead and summarize over here with the indeterminate forms. We've got these. Let's go ahead and add in our powers as well. Shrink that down a little bit so we can get them all on the same screen. And so we can go ahead and add in our powers now. So we've got 0 to the 0, infinity to the 0, and 1 to the infinity. So we end up with these 7 indeterminate forms, and we can go ahead and erase the thus far, and these are our summary of our indeterminate forms now. So we have all 7 of these. We've got our quotients. So listed first are the quotients, then the difference, the product, and then now we're adding the powers. So we're adding the powers today in this video. Okay, so how are we going to do this? Well, I mentioned we're going to have to apply some algebra. So how are we going to do that? Well, what we're going to do is we're going to consider the limit of this function, and we're going to give it a name. We're going to call it y. So we're going to take y equals f of x to the g of x. And if I want to break apart a power, the easiest way to do that is to apply a logarithm. So we're going to apply, so we're going to use those algebraic techniques. We're going to apply a natural log to both sides. And the reason for doing that, of course, when we apply the natural log, it's going to bring down that power. So notice on this side, I have now created a product rather than a function to a power. Rather than having a function with a power in the exponential, in the power spot, I now have a product of a function times the natural log of another function. And now when I take the limit of both sides, I'm going to end up with a 0 times infinity. All of those power forms, when I take the natural log of the base and bring down the function that is in the exponent, I will end up with something of the form 0 times infinity. So then I can just use the strategies that we outlined before, and we can compute this new limit. Now remember, because we took the natural log, in the end, we're going to have to undo that. Okay? So remember that in the end, we're going to have to go back and we're going to have to apply the fact that our y is actually e to the natural log of y. So we will have to undo in the end, here's the step where we're actually, after we applied the natural log, here's the step where we undo the log with an exponential. Okay, so in the end, we're going to have to undo that logarithm. Anytime you apply a logarithm to a function, then you have to undo that in the end. Okay, it's a little bit similar to logarithmic differentiation, where we use a logarithm in that case to simplify functions and take derivatives of functions. And we had to remember, by doing that, we then had to use implicit differentiation instead of just differentiating. So just have to remember that when we do it, we need to apply the appropriate strategies to the new logarithm. Okay, so keeping in mind these strategies, let's run through a few examples. So let's start with our first limit here, our limit of this polynomial x squared minus 4x plus 4 raised to the power of x minus 2 as x approaches 2. And so it might be useful, again, I had those indeterminate forms listed up at the start of the video, but today we're working with the powers, so I'm just going to list just the powers. I know there are of course all the other indeterminate forms as well, but just so we remember, 0 to the 0 is indeterminate, infinity to the 0 is indeterminate, and 1 to the infinity is indeterminate. Okay, so keeping those in mind, let's run this through. So of course, we have to, before we do anything, we have to check to make sure that the limit is in fact indeterminate. Otherwise, we should just evaluate the limit. So check to make sure it's indeterminate first. That should always be your step. So when we do this, let's see, when we plug in 2, we're going to get 2 minus 8 plus 2 squared, actually, minus 8. So we get 4 minus 8 plus 4 to the 0. Well, that is 0 to the 0, and that is indeterminate. And so once we found that we have an indeterminate form, then we have to decide, is it the form that I can apply L'Hopital's rule to, or do I need to do a little bit of work? And on this one being a power, since this is indeterminate form power, what we're going to have to do is we're going to have to use our logarithmic technique. So the first thing we're going to do is we're going to say, okay, let's take this and let's set it equal to y. Y equals x squared minus 4x plus 4, because I need to do a little bit of algebraic manipulation in order to evaluate this limit. Okay, so now I'm going to go ahead, and once I've done that, I need to bring that power down. I need to create a quotient, remember, so I can have that 0 over 0 right in my head. I'm like, I got to create that 0 over 0, infinity over infinity, so I can apply L'Hopital's rule. Right now I've got a power to a power. So I'm going to use that logarithm. By doing that, I now have that the natural log of y is equal to x minus 2 times the natural log of x squared minus 4x plus 4. Now that's not quite in a quotient yet, But remember, anytime that you have, we discussed this when we talked about those products, but anytime you have, side note, let's bring this over to the side, or just off to the bottom. Anytime you have f of x times g of x, if you want to turn that into a quotient, you can drop either of those two functions into a denominator by looking at the reciprocal. So we could write that as g of x divided by 1 over f of x, or you could write that as f of x divided by 1 over g of x. So that's a strategy that is useful for us whenever we are having a product that's indeterminate and we want to use L'Hopital's rule with a quotient. And so we can turn a product into a quotient by just utilizing division by reciprocals. Okay. So just that was a quick review. We discussed that when we talked more about the indeterminate form of the products. So let's come back here. So same thing here. I could run the limit through this right now. But if I were to run the limit through this right now, I'm going to end up with a product. I'm going to end up with a 0 times a negative infinity, actually. And that's still indeterminate. It's just indeterminate of that product form. And so before I even go back to the limit, I'm just going to do a little bit of work here. I'm going to say, let's say this is the natural log of x squared minus 4x plus 4 divided by 1 over x minus 2. I'm going to utilize that reciprocal rule. And better yet, before I even go back to the limit, better than even that, what if I just write this as x minus 2 to the negative 1 in the bottom, right? Remember the reciprocal, 1 over x minus 2 to the first power is the same as just writing x minus 2 to the negative first power. Just utilizing all our tools of algebra here. Okay, now I'm going to go back to the limit. So now I'm going to go back to the limit. Kind of keep track of what we're doing here. Back to the limit. Just adding a little extra letter right there. Okay, so let's go back to the limit. And this time, though, we're not taking the limit of the function. We're taking the limit of the natural log of the function. So we're going to take the limit. And I'm going to write that in, and you need to write that in. So you remember, you're not taking the limit of the function. You're actually taking the limit of the natural log of y, but that is equal to this. So we can utilize this form. So this is the limit as x approaches 2 of the natural log of x squared minus 4x plus 4 over x minus 2 to the negative first. Now, look at what happens when I take that limit. So we worked on that. We had that indeterminate form that was a power, used the logarithm to turn it into a product, and then a little algebra to turn it into a quotient. And notice what happens now. As we approach 2, this quantity inside here is going to approach 0, and the natural log of 0 is negative infinity. Notice on the bottom as we approach 2, this inside here approaches 0, but we're taking 1 over something that approaches 0. Okay, so the quantity inside here, but it's 1 over 0. So that is also going to approach infinity. And that is an indeterminate form. Notice it does have a sign on it, but the signs, when we have infinite behavior divided by infinite behavior, whether it is growing or decreasing without bound, it is still indeterminate form, and we can still apply L'Hopital's rule. So we can go ahead and apply L'Hopital's rule to this now. We are now in the quotient form by which L'Hopital's rule is valid. So now L'Hopital's rule can be applied. So we can go ahead and now we can take L'Hopital's rule. Again, my notation, and I do want to see some kind of notation in your work for when you do apply L'Hopital's rule. 1, you've got to justify that it's valid to apply L'Hopital's rule, and 2, you have to show that you're doing it. So remember, use a little notation. I like the little LH. I've seen just the H or even the circling of the equal sign. All of those are fine, but some sort of notation that you're applying L'Hopital's rule. So now we're taking the limit as x approaches 2, and remember L'Hopital's rule says take the derivative of the numerator and divide by the derivative of the denominator and take a look at that new limit, the derivatives, the limit of the rates of change, the derivatives. So in the numerator, we're going to end up with 1 over this quantity times the derivative of that quantity. So that's going to end up being 2x minus 4, the derivative of the inside, and then x squared minus 4x plus 4. So I took the derivative of the logarithm multiplied by the derivative of the inside and combined it. all at once. Now on the bottom, I'm going to get minus 1 x to the minus 2 to the negative second power times 1, derivative of the inside there. And then I'm going to continue to simplify. I'm not taking L'Hopital's rule again, nothing like that. I'm just going to simplify. I notice up in the top I could factor and write that as 2 times x minus 2 divided by x squared minus 4x plus 4 divided by, oh, you know what, in the bottom, let's go ahead and factor that bottom too. I notice that bottom also factors x minus 2 squared, and in the bottom I've got minus 1 over x minus 2 squared. Now I've got that crazy compound fraction, so let's get that simplified. So this is the limit as x approaches 2 of 2 times x minus 2 over x minus 2 squared times a negative x minus 2 squared over 1. And conveniently, look at all of this reduction, simplification. We've now got the limit as x approaches 2 of negative 2 times x minus 2 over 1. And now we can go ahead and take that limit. That limit now is simply 0. Okay? And what I will say is a common mistake is to box this off, all that work, we're done. But that is not true. That is not actually our answer. That is the limit of the natural log of y. So these, we need to keep track of what we're doing here. So let's carry, since I've moved to the bottom of the screen and I need to zoom in, let's carry this down. So this is the limit as x approaches 2 of the natural log of y. Remembering what we're actually looking for is not the limit of the natural log of y. We want to know what the limit of actually y is. So what I can do right now is I did all that work up above, so I'm just going to sort of, I'm going to focus in on this. I've just shown that these two are equivalent. What I can do is I can use an exponential on both sides here and all the way across the equal sign. By doing that, this comes inside the limit. This is now the limit as x approaches 2 of e to the natural log of y is equal to, I'm going to skip that middle step, we don't need it there, and e is equal to e to the 0. Well, the limit as x approaches 2 of y, because e to the natural log of y is just y, is actually equal to 1. And my answer is 1. I have to undo, at the end after I've calculated the limit, I have to undo the logarithm with an exponential. And if we've been careful with our notation, we can simply do that by writing our last step. And I kept my equal sign throughout. So I just jumped to that last step there and I said, you know what, I've just calculated what the limit of the natural log of y is. So if I take the exponential of both sides of that equation, I will end up with the result of my original limit of y. And we defined y right up here. Okay, let's go ahead and do at least one more. Let's do this guy. Let's do one more of these limits, I think, on this video. And we can see that process one more time. Okay, so once again, we're taking a limit. We've got a function raised to a function. So we've got x to the natural log of 2 divided by 1 plus the natural log of x. As x is growing without bound, goes to infinity. So what is that going to approach? Well, obviously x approaches infinity. Now the power here has a numerator of natural log of 2, and then we're dividing by 1 plus the natural log of x. Well, that's going to be infinite. 1 plus infinity is infinity. A constant divided by infinity is 0. So this is infinity to the 0 power. And infinity to the 0 power is, in fact, indeterminate. Okay? So remember, we listed those, all three of those indeterminate forms here, but we do need to know those. So 0 to the 0, infinity to the 0, 1 to the infinity. And we are getting infinity to the 0 here. So that is definitely indeterminate. So we're going to have to do something here. Not only is it indeterminate, but it's indeterminate in power form. So when we're indeterminate in power form, we remember we've got to use that little trick with the logarithm, right? That little algebraic technique where we can bring down the power so that we can apply it. So we're going to go ahead and say, let's just call y x to the ln of 2 divided by 1 plus ln of x. Let's zoom in just a little bit here. Then I'm going to go ahead and use the logarithm on both sides of this equation so that the natural log of y is actually, that whole power is going to drop down in front. Natural log of 2 over 1 plus the natural log of x times the natural log of x. Utilizing techniques of algebra here with logarithms and rules of logarithms, bringing powers down. Now what we can do is just simplify. There's not a whole lot actually to simplify on this one. We've just got that constant, ln of 2 times the natural log of x. So I'll just write it like that. And then divided by 1 plus the natural log of x. And notice on that front that this became a quotient simply through the simplification, right? On the previous example, we had to do a little bit of work, right? We ended up with a product, and then we had to do a little bit more algebra to create the quotient. This one, we have created a quotient. Yay! We created a quotient simply in that step of taking the log. So now I'm going to go back to the limit, okay? And I'm going to take the limit. Back at the limit was as we were approaching infinity, so we're going to take the limit as x approaches infinity of, and I always write this because I want to remember that I'm taking not the limit of my original function, but the limit of the natural log of my original function. But we just showed that that is equal to, just through a little bit of simplification, that is simply equal to the natural log of 2 times the natural log of x over 1 plus the natural log of x. Now it's a quotient, so let's go ahead and see what that limit is as x approaches infinity. And notice, as x approaches infinity, natural log times natural log of 2, which is a constant, times the natural log of x as x grows without bound. Natural log grows without bound. So we've got infinity over 1 plus something that's growing without bound, also infinity. And so that is indeterminate form, and we can apply L'Hopital's rule to this form. So now we're ready. We've got it in the quotient form that we can apply L'Hopital's rule to. It's the correct indeterminate form, infinity over infinity, or 0 over 0, where we can apply L'Hopital's rule. And so we can go ahead and do that. So take the limit as x approaches infinity. Take the derivative of the top. So we've got that constant natural log of 2, and then the derivative of natural log of x, of course, is 1 over x. Derivative of the bottom. The derivative of 1 is 0. Plus the derivative of the natural log of x is 1 over x. So we get 1 over x. And conveniently, those two factors cancel. And so we end up with the limit. Oh, no, well, I was going to take the limit, but we'll write one more step. The limit of just the constant natural log of 2, which, of course, remember, this is just a constant. So the limit of a constant is the constant. So we've got natural log of 2. So what we have shown right here is that the limit as x approaches infinity of the natural log of my original function is simply the natural log of 2. But that's not what I was looking for, right? I'm actually looking for the limit of the original function, which is y. So in the end, I need to use an exponential to undo the log, okay? To undo the logarithm. I introduced a logarithm, so I have to undo that. So I've got to use an exponential. I have to raise both sides of this equation into the exponent of an exponential e of the same base of this logarithm. By doing that, that exponential runs inside the limit. This is the limit as x approaches infinity of e to the natural log of y, which is equal to e to the natural log of 2. And then just properties of logarithms say that the limit of the original function, which we defined as y, just so we didn't have to carry it all the way through. So the limit now of the original function y, which is what we wanted, is equal to 2. And there's our answer. So let's go ahead and zoom all the way out. So the original function, remember, was that x to the, there it is right there, x to the natural log of 2 divided by 1 plus the natural log of x. And so we defined y right here and used that to follow this through and find the limit. But we have the limit now of 2. This last example, I'm going to save that last example for either a problem session or office hours if anyone wants to see additional examples, but similar process. So you would, again, identify that it's an indeterminate form, power form, utilize your logarithm tool to pull it down into a quotient form, and then take the limit and then undo the logarithm at the end. Okay, so just to summarize, so when we've got one of those indeterminate forms, power forms, which are the 0 to the 0, infinity to the 0, or 1 to the infinity, we utilize this process where we use a logarithm. Use a log to simplify. Okay? Use a log, simplify it. It will turn into a product, which we can then simplify in algebraic ways into a quotient where we can apply L'Hopital's rule. In the end, make sure that we undo the logarithm using exponentials. And that summarizes our L'Hopital's rule in all of our indeterminate forms. So I'll leave this last screen on. These are the forms we want to make sure that we have memorized, or that we somehow put down as a reference page where we can, when we're taking limits, that we can reference. So we'll know when we come across indeterminate forms and when L'Hopital's rule might be a valid approach to calculating the limit.